Hello, so today we will be talking about the impulse and conservation of momentum. These are the things that you had already learned when you were in high school, but let us have a look at them again. Last time we had seen about the conservation of energy, which states that total energy is always conserved. Today we will be seeing that the total momentum is also conserved if the system is closed, that is when there is no external forces and there is no exchange of matter between the system and the outside and outside of the system. So let us just go ahead first with what is impulse. Impulse, you may have remembered, I will not go into the details, but let me just give the mathematical definition of it, okay, in terms of equations. So the impulse, we used to say, whenever we say the impulse, we used to say impulse of a force. So that is why the impulse of a force F over time t is equal to, okay, it's given by this equation I equal ft. That is, the force is applied for a time t. But you must also remember that the force, it can be constant or it may be variable. So what happens if it is a variable force? This is when the force is constant, okay, when F is constant. But when F is not constant, if F is not constant, then what happens? We can assume that the force is again constant for a brief amount of time. So what will actually happen is, okay, F, we can treat it to be constant for a small amount of time dt. So the impulse will be I equal f dt for that small amount of time. But since we want for a large amount of time, we will have to integrate within the limits, okay, from 0 to t, if we want for a time t. Okay, but since we want from t1 to t2, okay, we can measure the time from any interval t1 to t2, then we can do this. We can simply write it as 0 to t also, it really doesn't matter, okay, but we just need two limits for the time. Okay, so this is it. What we are going to do now is we are going to show that the impulse is equal to the change in momentum. So by using this equation only, I is equal to t1 to t2 f dt. Again, you remember that f, it cannot be constant. What I mean is, it is not constant. If it is constant, you can take it outside of the integral sign, but over here it is not constant. So what we will do, we can write this one as m dv dt, because the force can be written as mass times the acceleration dt. So over here what we will be getting is m dv, but over here, since these are the limits for the time, but now we want the limits with respect to v, so we will be writing v1 v2. The mass, it's constant, so we will be getting m v1 v2 dv. Integrate this one, you will be getting v, which is the velocity, so you'll be having m v2 minus m v1. Hence the impulse is equal to the change in momentum. Okay, so we are done. mv, it is the momentum. So mv2, v2 is the velocity at time v2, it is the velocity at time t2, v1 is the velocity at time t1, so mv2 will be the final velocity, and mv1, it is the initial velocity, hence this is the change in momentum. What really happens if there is no external force? If there is no external force, that is, the external force is zero, so momentum will be conserved, or it will be constant. If that is, there is no external force, then momentum, it will be constant, because over here it will be zero. It will be zero, right? So it will be equal to zero, hence mv2 equal mv1. You should be careful. Over here we are saying external force. So what counts as an external force? It actually depends upon the problem, okay, because sometimes what may be counted as an external force for one problem, it will be counted as an internal force for another problem. For example, if you are considering the sliding of this pen here, when I push it in this way, then friction, you may consider it as an external force, or for some of you may consider it as part of the system only. Okay, so it really depends. So based on that, let us try to do this question right here. A gun of mass m fires a bullet of mass m horizontally. So that it is just sufficient to project the shot vertically to the height edge. Show that the distance through which the gun will recoil if resisted by a steady force equal to 1 by n of its weight is m squared nh divided by capital M, m plus m. So let us see what is happening. You are having a gun. My drawing is not so great. So this gun, it is shooting a bullet. The mass of this gun is capital M. The mass of this bullet is small m. You may have seen that you must not have experienced it, but surely you have seen that when you are shooting a gun, okay, what will happen is the bullet will be traveling in this way with some velocity. Let us call it v2. And over here the gun, it will also suffer a force. Okay, so some force will be, okay, which is called as the recoil. There will be a force, so we'll be moving in this direction, the gun, and that velocity, it is called as the recoil velocity. Let us call it as v1. So v1, it is the recoil velocity of the gun. v2, it is the velocity of the bullet. M is the mass of the bullet, and capital M is the capital mass of this bullet. So what is going on over here is that this bullet, it has some energy attached to it. Okay, that energy, it is, okay, the energy, first of all, the energy required to shoot this bullet, what is given in this question, the energy of the explosion, it's the energy required to shoot this bullet, it's equal to the energy to move this bullet to a height edge. Okay, equal energy required to move the bullet to a height edge. This is what is really happening. So the energy required to raise the bullet to a height edge, if you must remember, it is the potential energy. We can calculate it in terms of the potential energy, which is equal to the mass of the bullet times GH. So this is the energy of the explosion. It is required to move the bullet to height edge. Okay, equal energy sufficient. Okay, let us just write it as sufficient. So this is the energy of the explosion, and also afterwards the system, this is during the explosion necessary to shoot this bullet, it's equal to this much. After the explosion there will again be some energies attached to this system, which is the kinetic energy of this bullet and the kinetic energy of this gun. Okay, because the gun will be moving in this way. But first things first, we need to, and afterwards, what is happening? So there is a gun, it is exploding, okay, it is shooting a bullet, and afterwards this gun, okay, because there will be someone who is holding the gun, and he will be applying a resistive force to it. Okay, so this resistive force, it's equal to 1 by m times the weight of the gun. Okay, the gun will be moving in this way, but there will be a resistive force. You must remember that this force is only happening after the bullet has traveled, okay, after the explosion, after the shot has been fired. So now that we have understood what is happening, let us try to solve it. So this force, you must remember that it doesn't come into play before or during the explosion. It comes into play only after there is a recoil velocity. So let's see solution. When solving these problems, okay, we need to remember that since this system is closed, there is no longer an external force. Okay, you may disregard air resistance, which is an external force. Okay, so there is no external force. What we will say is by conservation of linear momentum, what is happening? The total momentum before the shot is equal to the total momentum after. Okay, so the total momentum before the shot nothing is happening, so the velocity is 0. The total mass of the system, it remains as m plus m. Okay, the total mass is m plus m. That is when the bullet is still in the gun and nothing was happening. The velocity, it was 0. It's equal to the momentum after the shot has been fired. Now m and m are traveling with different velocities. This mass m is traveling with velocity in this direction, and this small m is traveling with velocity in that direction. But you must be very careful over here, because remember that if you are doing any kind of problem in dynamics, you must first resolve all the velocities in the same direction. You can see over here they are in different directions. So when resolving this one to that direction will become minus v1. Okay, or you can resolve it in this way, it will become minus v2. You can resolve it in any direction that you like, as long as all of them, they are all in the same direction. So let's see. So I will write it as minus m v1, okay, because it is in this way, plus small m v2. So we will be getting mv1 equal mv2. v2 is the velocity of the bullet, v1 is the recoil velocity of the gun. You can just mention that. It's okay, it's not too much of a burden. You can do it. Now this is the conservation of momentum, and it has given us this first equation. Now what we will do is we will use the principle of conservation of energy. By conservation of energy, okay, if you have to say it in full, you must say principle of conservation of energy, but I hope it is clear. And over here you must say law of conservation of linear momentum. Okay, so the energy, it's equal to E, which we have given over here the energy of the explosion, the total energy before and total energy after the explosion. This m, it will be traveling with half m v1 square. Okay, even if it is a negative sign, after squaring it, it will become positive. Okay, so that's why I've written it directly like this, half mv2 square. But E, it's equal to mgh. Multiply this 2 over here, you will be getting 2 mgh mv1 square plus mv2 square. What can we write here now? Okay, let us leave it like this first. Actually, if you notice the question, okay, we have to do something else. We need to take into account this force. Okay, so this force, it is only related to this velocity v1. So what I will do over here, maybe I won't need this v2 anymore. Okay, so that's why I will express everything in terms of v1. Okay, because v1 will still be related to this force that is happening afterwards. So over here, I can substitute v2 in terms of v1 here. So m v1 square plus m v2 square will be mv1 upon m whole thing square using 1. Again, I am expressing it in terms of v1 because maybe I will need this velocity again. So let us just try to simplify this. So you will be getting 1m over here, so you will be getting mm v1 square, divide the whole thing by m, plus m square v1 square. So you can take common again m, then you will be getting m plus m v1 square divided by m. I think over here we will still be getting one more m. So let's okay, actually no more m. So this is what we will get. Okay, this is what we will get. So again, we can just do like we did before. Okay, we can take common capital M. And over here we'll be getting m plus m v1 square upon m. Just name this one as equation 3. Let's hope I did not make any mistake. Anyways, we can always correct it. So now what we will do is, now after the explosion, this gun, it is traveling with velocity v1, it's in this direction, and there is a resistive force F. The resistive force is equal to 1 by n mg. This resistive force, it's necessary to stop this gun. Okay, so this gun, it will be traveling to some distance. Okay, just like when you are holding a gun, you will shoot in this way. Okay, if I am holding a gun like this, so I will travel, my hand will travel some distance. I am also applying a force, otherwise it will hit my face. So something like this, it will be traveling some distance. So let this distance be x, let us call it. The gun travel for distance x. The velocity, so it reduces from v1, it reduces to 0 because it's stopping like this. Okay, now after the shot is fired, resistive force experienced by the gun is F equal 1 by n times its weight. So it's this one. Now what will happen is we can use the equation of motion. Hence, its equation of motion m d2x dt square. Okay, so this is the force experienced by the gun. It's equal to minus half mg because it is a resistive force. I don't want to erase this equation 3. So over here again we can write, sorry, this is capital M. So we can write this one as v dv dx. (1 by 2g). We can integrate v square upon 2, the limits from v1 to 0, minus 1 by 2 gx. It travels a distance x. Okay, maybe let us call it d. Let d be the distance traveled by the gun. So you will be having 0 minus v1 square equal minus gd. So v1 square, it will be equal to gd. I hope I did not make any mistake. Sorry, this is 1 by n. Okay, I made a mistake. This 1 by n. It's not 1 by 2. So over here we'll be getting minus 2 gd by n. We will substitute this one here. What we will get, substituting in 3. Substituting v1 square in 3. So we will be getting 2 gd upon n. So 2 and 2 will get cancelled. G and G will get cancelled. So all that will be left. D, it will be equal to m square n. M square n h divided by m plus n. So this is the required expression. So if you can see what we are using, we are just using the principle of conservation or the law of conservation of momentum and the principle of conservation of energy to solve these problems. Then later on, if distance is involved, we can even use the equation of motion which is experienced by the particle, the gun or the bullet, depending upon the question. Until next time.